Good afternoon, everybody. I'll give everyone a second to join. Hope you all have a lunch in front of you. And we got an hour today to talk about DOAS, ventilation, and outside air systems. So I'll give another 30 seconds for everyone to join. All right, let's get started. Today's topic number 4, right? This is the 4th presentation we've had in our webinar series. You can go back on our website, ceshv.com, and check out all the past recordings. This presentation will be posted onto our website as soon as the presentation is done or later this afternoon. So without further ado, DOAS, ventilation and outside air systems. If you've joined other sessions, you know this spiel already, but my name is Jack Corcoran. I am the VP of Engineering at Caton Energy Solutions. We are an equipment manufacturer's rep, so we help engineers get equipment selections, cut sheets, and we provide that equipment to the end user. You can always reach out to me for selections on various types of equipment you might have in a project. I got my bachelor's of science in mechanical engineering at the University of Notre Dame. Go Irish. I am now a licensed professional engineer in 3 states. And before I joined the Caton Energy Solutions, I started my career as a design engineer. I was a mechanical engineer at AMA Group USA, which is now CMTA, which is where I got all my experience to be able to get my professional engineer license. So where does this session sit in the series? We have today is DOAS, ventilation and outside air systems. Next week, we're going to be talking about gas detection fundamentals, which loosely ties into this presentation today. And then the following week is about large warehouse HVAC and how that might be different than a commercial office building. And as always, I start off the presentation with a promise, right? What are you going to be able to do by the end of the presentation? Number 1, you're just going to be able to identify a few different outside air system types and how they deliver the outside air into the occupied space. Number 2, you're going to understand the heat transfer principles of the different outside air systems and how each one takes advantage of its own components to be able to deliver that outside air at a temperature you need. Number 3 is list the advantages and disadvantages of our outside air systems. And the 4th one is determine which outside air system should be used, right? And we'll go over a few examples and determine which type might be best for that application. So the ventilation requirement, right? How do we know how much outside air, right? Every project requires outside air per code. It is in the New York State Mechanical Code or New York City Mechanical Code, all derived from the International Mechanical Code. But there's a table in Chapter 4 that has all the outside air rates per occupancy type. So basically, you're delivering a certain amount of CFM per square foot and then a certain CFM per person in the occupied space. That total, the equation at the bottom, you see there's 2. The top one is that equation, right? You get those rates of the CFM per square foot, your CFM per person. You calculate out with based on how many square feet and people you have, and you get 1,000 CFM or 10,000 CFM, whatever it ends up being. That is your code minimum, and you have to bring it into the building. We're bringing it in per code, but really in reality, the driving forces are indoor air quality. You don't want stagnant, stale air, and different occupancy types might require more or less conditioning or fresh air to be brought into the space. So in addition to the minimum set by a code, right? If we have a lot of exhaust air in our space, you're going to also need a lot of outside air. Our mass balance equation is at the bottom, right? If you need to sum up the air going in and the air going out, and they should equal each other if as long as your pressure is the same, right? Or at equal pressure. So if you have a system that requires a significant amount of exhaust, you need to make sure you provide outside air into the space so your balloon doesn't deflate with all the exhaust going out. You need to make sure you're pumping in as much air as you're exhausting. So that also is a factor in what determines the CFM of our outside air. And then lastly, demand control ventilation. I'm just going to touch on it. It is a much deeper topic, but essentially the first two are fixed values, right? You're going to end up with a solid number. But energy code requires demand control ventilation for certain occupancy types. And essentially all it is it allows you to modulate the amount of outside air you bring into the building. In that first equation for the CFM, you have an outdoor rate based on the number of people, and you have it based on the number or your square footage. So if you don't have as many people in the space, theoretically, you can reduce the amount of outside air CFM you're bringing in, and that's exactly what demand control ventilation does. It's just a modulating CFM of outside air instead of a fixed value, and that, as we'll see, has energy saving implications. Just because you're not cooling all that hot and humid or very cold and dry air. Right, so we're bringing in all this outside air for code reasons, makeup air reasons, mass balance, and it's required, but it also carries a heat load with it, right? Our occupied space is in the middle of the screen here. It's our 75 degrees, 70 to 75 degrees Fahrenheit. If you're bringing in outside air, unless it's exactly 75 or in that range, you're going to be adding a heat load to the space, right? If you have on the left side a very cold winter day at 0 degrees in New York, we know it can definitely get to 0 degrees. You have a lot of cold air coming into your building that you'll have to heat up, right? You have to spend energy to heat that air up, and you're also bringing in all that dry air, which may have negative consequences if your space can't be super dry. Now, the flip side is also true. If it's a really hot summer day, you're bringing in a lot of hot and humid outside air into your 75-degree space, which we don't really want to do. Otherwise, in both situations, our indoor air is going to be, not very comfortable for our occupants. So we need to make sure we account and plan for this sensible and latent load that we're adding into our space. And back to our theme of all of our presentations, right? If we're adding in a heat load, how are we going to move that heat back outside, right? If some way, some combination of these 5 system loops, as introduced by Train in their HVAC clinic, we're adopting it here because it's a really good way to explain these sorts of systems. The 5 loops are along the bottom. Which one are we actually going to be using for our outside air, right? Are we going to which combination, 1, 2, 3, or more? We can actually use any combination, right? But primarily today, we're going to focus on just the air side of things. We have a lot of other topics and conversations and presentations about different types of equipment, but today, because we're talking about outside air, right, we're going to focus on just the supply air loop. But as we all know from some of our previous presentations, we do need to have a cold coil, right, or a hot coil in order to cool or heat our outside air load that we brought in. So while we'll focus on outside air, we do know that we're going to have these other loops involved in some way. So what type of outside air systems can we actually go with, right? Are we going to just bring it in with an outside air fan, right? Maybe we'll use an ERV to slightly temper the air, or maybe we need a full-on DOAS unit that uses mechanical heating and cooling. These are, I guess, a simplified version of the types of systems you can use. There's quite a wide variety, but essentially, this is your low, medium, and high levels of tempering your air before it reaches your space. If you start at the top here, right, our outside air fans, there's no coil in this, right? It just brings the raw outside air into your space. And as we said, maybe that's not ideal on your hottest days in the summer or on your coldest days in the winter because it carries a significant heat load with it. Moving down the list, right, you can use an energy recovery ventilator or an ERV. Sometimes, or there's another type of equipment called an HRV, a heat recovery ventilator. Both of these systems operate, it passes your exhaust air over the outside air stream. And essentially, right, if your outside air is at 95 and it's hot, your space is at 75, but you need to exhaust it, you essentially just run your exhaust air past your outside air, and that 75-degree air cools down your 95-degree air slightly before it enters into the space, right? It's not a perfect system, but it is free, right? We still don't have a coil. We're just simply transferring the air past each other in and a wheel or a plate. We'll talk about that in a little bit, but essentially the two air streams pass over each other and transfer the heat so that it's better than an outside air fan because you're not just bringing in the raw outside air, but you are slightly cooling and tempering the air as you bring it into the space. And lastly, you can use a full-on DOAS unit, right? DOAS stands for Dedicated Outside Air System. This is where you're going to have your mechanical cooling and heating, right? You're going to have some sort of heat pump. You're going to have your DX coil. You're going to have a chilled water coil. You need to add in work in this phase. This is your mechanical cooling with our compressors, right? This is going to allow you to get your outside air to whatever temperature and humidity you need, right? If you have a very strict requirement on your temperature and your humidities, you're going to actually need to put in work, right? You got to add energy in order to get rid of that, added latent and sensible heat that we're bringing into the space. So our three systems: outside air fan, ERV, and a DOAS unit. So this is just another way of taking a look at it, right? We can bring in the outside air directly into the space, right? This way, as we said, the outside air dumps the hot and humid 95-degree air on the left side directly into our occupied space. You're going to have hot and humid space. That's just the way it is with an outside air fan, but it's easy, it's simple. There's nothing cooling or heating up the air. An ERV on the top right, we're going to bring that outside air at 95 slightly down. In this case, an 81-degree temperature with slightly less moisture in it, and only 3 droplets instead of 4 that we had with the outside air fan. And then lastly, your DOAS unit is bringing your 95-degree air down to space neutral. It is bringing it to that 70-degree and not super moist or wet air. It's just comfortable for the space as it needs, right? You can adjust. It doesn't have to be 70. It can be any temperature based on what size you have your capacity of your DOAS unit. And so this is dumping it directly into the space. That's one way to do it. A little bit more common way to do it, right, is not to dump the outside air directly into the space with a diffuser. It's to funnel that outside air into a mechanical room or into a secondary downstream air handler that serves that individual room, right? And so in this situation, you're mixing the outside air with return air, and then it passes over a coil as it goes down downstream, right? So if you start on the left side of the screen here, with your outside air fan, 95-degree air doesn't change temperature or humidity as it goes over the fan blades, but maybe your indoor unit right within the middle box can handle that 95-degree wet air and deliver that into the space perfectly fine, right? It's the same situation for our ERV, right? In this situation, however, we can downsize our unit that's in the box, right? Maybe you don't need as big of a coil because you don't have 95 wet air coming over it. You have 81 and slightly less wet air coming over it, right? And then the last thing is your DOAS unit. This already has a coil, right? We're already putting in work. So that means we're going to have this, we're going to be able to downsize that indoor unit in the occupied space as much as possible. That unit isn't going to have to do much lifting. All it has to do is, temper the return air that's coming in and mixing with this 70-degree air. But yeah, as we said, right, the two ways to provide your outside air into your occupied zone is directly into the space or as mixing it with return air into a downstream coil. So that was section one, right? We looked at the different types of outside air systems and how they deliver the outside air into the space, right? It goes directly or it mixes with return air. And, we got our ERVs, fans, or just our DOAS unit. So we'll move on to section two. How exactly do these outside air systems transfer heat? So the first thing we have to talk about, right, is psychrometrics. When I first looked at a psychrometric chart, I got dizzy and I never wanted to look at it again. It looks very complicated, and it can be complicated, but for the purposes of today, there's really just some simple trends that we want to look at, right? And so I circled the three axes that we really care about. Our dry bulb temperature is along the bottom. Those are vertical lines. So basically moving left or right, you're changing your sensible heat, right? And so if you just change the temperature and you don't move up or down on this chart, you're only changing sensible heat, and that's the dry bulb temperature. Now, if you go to the vertical axis and you look at the humidity ratio, that's where the amount of moisture in your air is determined, right? And you can see that that's your latent cooling and heating, right? And so your air temperature, right? If you know what your air dry bulb temp is and you know what your air humidity ratio is, you can plot it on this chart and you can figure out the other properties such as your enthalpy, right? Or your humidity ratio, right? Or your relative humidity percentage. So this chart is pretty powerful. And if you know just two of the properties of your air, you can chart it on here and you can find out your other pieces of information. The equations at the bottom here are pretty helpful for when you're sizing your coil or you're trying to figure out how big of a capacity you need for your unit. There's a sensible heat equation, there's a latent heat equation, and then your total enthalpy. Right, and that's just the diagonal line on the left side of the chart. So it's just a combination of the vertical and your horizontal axis. But basically, these equations are, the sensible one. As we can see, the last term is your dry bulb temperature, right? And that's what dominates that sensible heat. Your latent heat is the last term, right? That's your humidity ratio. That W is in grains per pound. It's just another way of measuring the moisture content, right? And it's just CFM and your dry bulb CFM and your humidity ratio. And then your last thing is your CFM and your enthalpy, right? So if you know your CFM that you required, right? Because we have our outside air CFM that was determined by code or by makeup air and mass balance. We know the CFM. If we can put it on a chart like this, we can figure out our sensible, latent, and total heat that we need in order to cool or temper it to whatever desired temperature we need. So this is a good chart if you want to look at it, and then the equations are helpful for determining your loads. Another important piece of information is our mixed air, right? And so we said there's two ways to deliver our air into the space, and one of them is mixing it with return air, right? So if our look on the chart here, RA is our return air, OA is our outside air. I plotted our 95-degree outside air along the bottom axis. The dry bulb is 95, and then if you look at the wet bulb, which is the diagonal lines on the left side, that's at 75. So our outside air is 95, 75. In New York, that's pretty close to the peak enthalpy day that you're going to achieve, and most of the time you'll be sizing your coils with that as the outside air temp and wet bulb. And then your return air is going to be somewhere in the 70 degrees and 50% relative humidity. I plotted those 2 points. When you do mixed air calculations, you just draw a line between the 2 points, and depending on how much outside air versus return air you have, that 0 to 100% return air or mixed air determines exactly what your mixed air temp ends up at. It's going to land on that line, and it's just a percentage, and the equations are listed here on the bottom. If you just know your CFM total of your outside air and your return air, and then you know your temperatures and your humidity ratios, you can figure out exactly what the mixed air temp is going to be, right? And that's a pretty powerful tool for us engineers to be able to use. You got to size your unit for the entering air condition and then the leaving air condition, right? So if we know the mixed air temp, we know what the entering temp is and how much maybe humidity or temperature, I guess, are sensible and latent loads that our coil needs to handle. So again, you can just plot your outside air, your return air temperatures. If you know your CFM, then you can find exactly what that mixed air condition is going to look like. And then lastly, sensible heat ratio is an important term that we need to know as engineers as well. This essentially, if you have a room, I guess, what is sensible heat ratio? It's going to be the ratio of how much sensible heat to the total heat in your space, right? So your internal heat, your internal space, your occupied space has several sources of sensible and then sources of latent heat. They're listed out here, right? Your sensible heat gain comes from your lighting, any piece of equipment, people give off sensible load, solar loads, exterior walls, etc. That's your temperature, not your moisture. And then your latent heat is comes from your outside air, right? People give off latent loads for like sweating, or just people give off both sensible and latent loads. Cooked food gives off latent loads. Appliances like a coffee maker, and then like plumbing, if you have like a pool or sinks with water and whatever, that adds latent loads into your space. So depending on like if you add up all your BTUs of your sensible and all your BTUs of your latent, you can use the equation at the bottom and you can figure out what your sensible heat ratio is. Basically, it's 1 if you have no moisture in the space, and it's closer to 0 if you have no sensible. It's all latent load. Now that being said, if on a psych chart, basically that line of your sensible heat ratio is on the right side of this psychrometric chart, and you can plot that line through your whole chart for every sensible heat ratio, depending on what your specific room's sensible heat ratio is. So if we know we have a 70-degree room with 50% relative humidity, if there was no latent load, that on the psych chart would move directly to the right. But we see here this sensible heat ratio is 0.7. So we're actually, if you don't have any heating or cooling in the space and your sensible heat ratio is 0.7, your 75-degree air with 50% relative humidity is going to increase in temperature and increase in humidity at that ratio, right? And you can just find that along the line that you drew of your sensible heat ratio. And this equation is pretty powerful, right? And so you can imagine the same thing can be said for if we're dumping our supply air into the space, right? And if we dump the supply air, which is our leaving air temperature of our unit, into the space it's at 40 degrees Fahrenheit, right? And you let it slowly drift up along this red arrow, that is going to allow you to hit that 70-degree space and 50% relative humidity, right? If you had a greater sensible heat ratio than this, if it was closer to 1, you'd have less humidity in your space. Maybe you don't deliver your supply air that low. You know that the sensible heat ratio is going to drive you across horizontally. You can actually deliver your air at 50, or maybe 55 degrees Fahrenheit, because you don't have to overcome that extra latent load. There's a really good video online that Captive Air does. This image is actually from that presentation that they have. Very, very helpful. If you look up psychrometrics and captive air on YouTube, they have a great video. Highly, highly recommend watching that because we can't really dive too much into it today. But sensible heat ratio is important for determining what does our supply air temperature need to be, right? Our temperature and our humidity need to be. Right. And so when we look at these, with these principles in mind, we can look at our different types of systems, right? We have our outside air fan. There's zero sensible and there's zero latent cooling, right? And so if you can picture the psych chart, we're only moving, we're not moving our outside air from 75 or 95, 75 anywhere along the chart, right? Whatever the sensible heat ratio of the space is, we're going to move along that diagonal line. If you go back to this chart, instead of having our supply air being way, way down to the left of the chart, it's going to be way high up on the right side. It's 95 degrees dry bulb. You move to the right and then you move up to 75-degree wet bulb. It's going to be a very, very warm space. And, intuitively we know that, right? If we're just dumping hot, wet air into our space, that raw outside air is going to cause the room to get hot and get, high humidity. It does have its advantages, right? If you don't have a very tight, if you're conditioning a warehouse, right? People aren't really in that space expecting to be at a very comfortable, temperature. Of course, maybe we want to shoot for that, but in all reality, most warehouses are just dumping outside air into the space at the required minimum ventilation. And, they're comfortable with the air getting up to, 95 degrees. That space can get hot in the hot days of the summer, but they are fine with that because most of the year, maybe the outside air isn't as hot or as cold, and they can get away with not tempering it. So it's a simple solution. It doesn't really temper the air very well. And so we can, again, dump it directly into the space. That doesn't really help us with cooling or heating it up, right? It just becomes the temperature of the outside air. Or we can dump that into a return air mixing box with a mixed air temperature, and then we just pass that load on to another coil downstream. Now we can talk about the ERVs, right? Our energy recovery ventilators. These partially temper, right? A little bit, looking at it a little bit closer, right? You can see these arrows. If you follow the blue on the left side, it goes into the unit. That's our outside air. It passes through that box, which is, the heat exchanger, and it essentially captures the heat from the exhaust air, which is the orange coming in from the top right, so that you can deliver a more neutral temperature into the space, right? Our sensible cooling and latent cooling is like a yellow color here. It's not blue, but it's not hot red that we had in our with just the fan. It's somewhere in between. But again, as we said a little bit earlier, it's free, right? We don't have to have a DX coil. We don't need a compressor. You're simply just passing the air over each other in order to just capture or recover that heat, right? And so, there's energy recovery ventilators, right? They're ERVs. Those can be wheels or plates. Essentially, the air mixes in different ways depending on how, much latent or sensible heat you want to do. If you do a wheel, you're going to get both because some of the air actually ends up touching each other and the moisture can cross between the streams. But if you only want to do sensible transfer, you can keep those air streams completely separate with a non-permeable plate, right? And these two streams will just pass through each other or pass over each other without touching. And the only heat transfer is sensible, right? You don't get any moisture that passes between the two streams. It's just the sensible dry bulb temperature change. And just like our outside air fan, right, we can dump it directly into the space, right? Maybe our space does not need, right? We wanted to get rid of 95-degree hot, humid air. We land somewhere in the 81 degrees air. Maybe that's more acceptable to be dumped directly into the space, right? More often than not, ERVs dump into a mixing box and then go into a downstream coil, right? And so that all that does, as we said, lowers the capacity required of your downstream coil, right? You don't have to do as much of a lift because you got some free cooling and heating and dehumidification with the ERV. And then, we have our DOAS cooling with dehumidification, right? And so the primary purpose of this DOAS unit is to dehumidify, right? On the psychrometric chart, we're moving that heat down vertically, right? We want to get rid of the moisture as much as possible, so that if we dump it into the space, you're not going to have any humidity issues. Or if you dump it into another coil, then that coil, this downstream coil, doesn't have to worry about humidity. It just has to temper the air temperature, dial it in per zone. So your DOAS unit is going to get on the left side, we're going to get that light blue, that very cold, sensible cooling. And we're also going to get latent cooling, right? All that moisture comes off the coil. It's going to condense. Uh, the the main difference between like a DOAS unit and a regular air handler is that the coil temperature is much, much lower, right? We want to put the coil temp much lower than the dew point so that we can whisk and wring out the moisture as much as possible, right? A colder coil means more moisture removal, right? And since outside air is very, very latent, we have to have that cold coil in order to achieve that latent cooling, right? But with a colder coil, right, we're going to overcool this, right? If we have a leaving air temperature of 40, 45, 50, that air, if you dump it directly into the space, is probably going to give you some issues, right? If that cold air blows directly onto, a cold metal surface or onto a window or something, that surface in the space also gets lower than the dew point of the space temperature, and you're going to get condensation on your windows. You're going to get condensation on cold surfaces, and that potentially, that definitely would be a bad problem to have. You got to be careful with how much you overcool, and sometimes it's a balance. Or maybe you just dump it into a mixing box of a downstream coil, and then that system, that super subcooled air mixes with warmer return air, and then you're not, maybe you're not delivering that air at below the dew point anymore, and you don't have the condensation risk. So this dehumidification coil is super, super cold because we want to get rid of all that moisture. And we actually end up overcooling it sensibly just because we're trying to do so much latent removal. And again, right, this is our mechanical cooling. In the top right, we see we got to put work in. This is not a free step, but it allows you to get, those super tight humidity requirements that you have in a lot of spaces. And we talked last week in the rooftop units, right? You can have a reheat coil. So if you need to get rid of the humidity and there's a lot of it in it, let's wring it out, get that coil temperature super, super cold, and then you can reheat it back up sensibly. So that reheat coil is downstream of your cooling coil, and all it does is combine. You see underneath the image, your sensible cooling, your latent cooling, and then you have sensible reheating. That reheat will drive that air temperature, to any temperature you really need without adding in humidity. You're going to maintain the same number of grains per pound on our psych chart. We're going to move directly left and right. But as I said, we're not going to be delivering that cold sub dew point temperature air into the space, and there's no risk of the condensation anymore. And essentially, this is very, very powerful if you're dumping the air directly into the space, because right, you wrung out all the moisture, and now you're delivering the temperature into the space at a neutral air temperature that isn't going to cause an extra load into your space, right? You're delivering it neutrally into your 70-degree and 50% relative humidity room. And we talked a little bit about the different ways to do reheat. You can do hot gas reheat, is probably one of the more common ways to do it. If you have a DX system or a refrigeration cycle, you're going to be able to recover that heat from the compressor discharge, and it's free, right? You already have that heat in the system from the space, Your refrigerant is just redirected downstream to a second coil, which is where we reheat it up. Or you can just use electric resistance. You can use hot water, steam, or gas. Really, any source of heat is going to be, it's possible to use that for your reheat. However, hot gas reheat, a lot of the time just comes bundled in with your unit and you don't have to think about sizing it. And right, so those were the three systems, but right, what if we combined some of them, right? If we are able to, like, if we need a very energy efficient solution, we want to use as little cooling energy as possible, right? So if we can drop the temperature of that outside air before it even reaches the coil, let's do it, right? So if we can combine the ERV and a DOAS unit together into one large air handler, we can get that pre-cooling with that yellow temperature right on the bottom left. We get that yellow sensible cooling, the yellow latent. And so that 95-degree air isn't 95 anymore before it hits the coil. It's 81 and a little bit less, latent driven. So um, after that, you can pass it over the smaller cooling coil, and then you can do sensible reheating if you need to. This is a very powerful way to cut your energy costs, right? A lot of the times, this is actually required by energy code, or a very powerful way to comply with energy code because you get that free cooling before you hit the mechanical cooling requirement of the DOAS. So lower energy than a regular DOAS, and you achieve the temperature and humidities that you want at a precise level. And you can deliver this air directly into the room, or you can mix it with a return air in a downstream coil. So we just went over section 2, right? We looked at our different types of outside air systems. Let's take a look at when each one might be advantageous or disadvantageous to use. So maybe this list is not perfect for this application, right? We're asking more so about our outside air and our ventilation. It is required by code. So some of these, you kind of just got to live with some of the consequences of that, right? I made a couple other lists that are a little bit better, more direct for our system. So what about outside air fans, right? We've talked a little bit about the advantages and disadvantages, but here they are laid out for us. So it's super cheap, right? You don't have any mechanical cooling. There's no expensive compressors or components. It's just a fan and a louver that brings your outside air in. You don't have any controls. There's no like temperature changing. It's just bring in the outside air at the amount of CFM you need. And there's no complicated coil, no refrigerant, no wheel or plate recovery media that you need to service every once in a while. A disadvantage, right? You don't get any tempering. There's no cooling or heating. Raw outside air enters your space. Maybe that's okay. Maybe that's not. Most of the time, that is a disadvantage, though. But if you're not dumping it directly into the space, you are just handing that outside air load downstream to that secondary coil, right? You're mixing it with the return air, but that load still needs to be captured by that downstream coil, which results in a larger coil downstream. And whereas the other types of systems we're looking at, you don't need as big of a coil and that downstream system. And you're going to fail to hold a tight space temperature and humidity. You're kind of subject to whatever the outside air temp and humidity is because you're bringing that in directly to the space. So in the bottom right, our best fit is a loose space temperature and humidity requirement. So like a warehouse or a garage. And it's best if you mix the outside air with the return air ahead of another coil that is sized for that load, just so you don't dump in the raw outside air to your space. And what about our ERVs, right? So some advantages of this, you get free energy, right? You get to recover up to 70 to 80% of that energy from our outside air or from our return air transfers into the outside air and allows us to, downsize the coil downstream. So that's that second point. If you can lower that 95-degree temp air to 81, that's a significant change in your coil size and you get a lot of cost savings, right? That free energy is great to reuse here. And a lot of the times your energy code credits, right? You can maybe hit high efficiency margins, or maybe get there's different programs for high efficiency equipment. ERVs are just really a great way to use to capture and reject and absorb heat without mechanical cooling. But the disadvantages are that you have some fan energy, right? You're gonna have pressure drops. Instead of you have to run your exhaust air through this ERV. So if that adds a pressure drop that you didn't have if you just dumped it out through a louver. Potentially in a large building with high CFMs, that could be significant in operational costs. This is a higher, first cost than the outside air fan, but it is lower first cost than the DOAS system. So it is really just comparing whatever options that are available for you. You're going to have some maintenance with your energy recovery wheel, potentially, just more points of failure than just having a duct go through a fan, pull the air through the duct. And the last disadvantage is while it is free, right? It's great that it's free. It doesn't do a perfect job tempering the air. It only lowers it to like 81. I mean, if it's even hotter than 95 out, you're not going to get even 81. You might get 85 or higher. So you're still going to have to temper the air if you do have tight space temperature requirements and humidity requirements. It can't act on its own. So where is it a best fit? It's a best fit if the coil you already have installed downstream, or you're planning on a large coil downstream, if that can handle your 81 and somewhat like moist air, you can use an ERV. It's great. You don't need to use a DOAS unit to get it super cool and dehumidified. You can just use an ERV, free energy, and that dumps into a downstream coil that can handle the load. And it's also really good if you're looking for energy credits, or if you need to hit an energy efficiency target. And lastly, our DOAS, right? We have an extra green box on this screen because DOAS have a lot of advantages, right? We're going to be able to hit any supply condition that we want, right? We can size our coil to deliver that subcooled, dehumidified air, and we can reheat it back up. It's great. You can pick your controls to be whatever discharge temperature and humidity you want. You get a full latent control. You're going to drive that supply air below its dew point, wring out all the moisture, and you're going to be able to deliver that air, without any moisture load or latent load into your space, because it's much better than just dumping the outside air with a fan or using the ERV. You actually completely remove the moisture, and that latent load drops to near zero. You get a dedicated delivery, right? So if you can deliver this directly into the space. You can get neutral air that doesn't add any heat load into the space, as I just said, right? It can go directly into the space without needing a downstream coil. And it also, you can have, I guess this last point is more important for like VRF systems, right? We talked about how they don't handle latent loads very well, right? They don't achieve a super low coil temperature all the time because they can vary the speed of the compressor and you don't get as low of a temperature. Essentially, DOAS is required when you use a VRF system, because your VRF system is not going to wring out the moisture if you use an ERV or just dump the outside air into it. You'd have to figure out, or have a very low amount of outside air if you wanted to use an ERV or outside air fan with a VRF system. So essentially, it allows you to have your secondary coil be sized for sensible, and this DOAS unit will be sized for the latent load. But it does have some advantages. It has a much higher first cost, right? This is going to be an expensive piece of equipment, but if it's required and you need it, you need to have this piece of equipment that can deliver a precise temperature and humidity into your space or into the downstream coil. You do have, your reheat. You are going to overcool because you're removing the humidity, and you need to have a reheat. That is, potentially, that definitely is an energy cost, right? You are reheating the air you just cooled down, right? And that can seem like that's just an energy use that you have that, wouldn't be required if you use one of the other systems. That just brings it slowly down in steps. This, you overcool it and then reheat it back up. It's less energy efficient. And the last point is you have to use mechanical cooling, which requires energy. So the best fit for this DOAS type of unit is when you have tight space temperature and humidities in your space, right? You need to hit that tight target. You need a DOAS unit. Or this is best for when you have a strict entering air condition, like a VRF system, right? It can't handle the high latent loads. So you handle the latent load with a DOAS system. All right, so we just looked at some advantages and disadvantages. So let's do some examples. Example A, right? So a warehouse, it's 300,000 square feet and it's in Edison, New Jersey. We are not looking to have a super tight temperature and humidity. As we said, it's a warehouse. There's, it's not an office. You can let that temperature of the warehouse drift up in the summer and you can let it drop lower in the winter. The owner does not want to spend a lot of money on the HVAC. They just need the code minimum ventilation, right? And the minimal exhaust. So you're looking at this project. What type of outside air system should we use? You can just use an outside air fan or a makeup air fan in this situation, right? You don't need to temper the air. There's no tight temperature requirement in the space. We can let that air in the warehouse go up to 95 degrees. It's not super important that boxes are maintained at a room temperature that's comfortable for people. You can let that temperature slide a little bit in the summer, and you don't need to spend all the money that you do on an ERV or a DOAS system. Example B, right? So now we have a VRF office building. It's 60,000 square feet, multi-tenant in Stamford, Connecticut. And we know that the system that's going to be throughout the space is a VRF system. And we need to bring the outside air to each of the zones. So we discussed just a little bit earlier and in our previous presentation on VRF that the VRF evaporator coils, the fan coil units, they can't handle the latent load. So you need a system, DOAS system or fan system that can provide that latent cooling before it gets to this downstream coil. We're going to have many, many zones, and there's minimal exhaust. And each of these zones has a tight temperature and humidity. It's an office space, right? You can't have people, in a clammy, wet, cold environment or very warm or dry space, right? You want to be comfortable. So what type of outside air system we want to use? We're going to do a DOAS system, right? And so that is driven entirely by the VRF system, right? You're going to need an outside air system that can get rid of the latent load before it reaches the VRF coil. So whenever you hear VRF, you're pretty much going to need to have a DOAS system. The only time I will say you can use an ERV if your mixed air ends up being very, very low percent of outside air. So if you only need like 25 CFM of outside air, but you need like 1,000 CFM of return air, that very, very latent load is potentially handled by your VRF system. So you just got to check the manuals. All VRF systems can handle some latent load, but on any of your hottest days of the year, right, you're gonna need a DOAS system to handle that. So example C. So we also have an office building here, but we have central air handling units, right? So we have 40,000 square foot office in White Plains. The building zones in this situation are cooled and heated by a central air handling unit system. So what are our dominant constraints? We have our outside air is mixing with our return air, right? Our air handler is going to be located in a mechanical room, and you just dump your outside air into the room or into the mixing box of your air handler, and that outside air is going to mix with the return air before it reaches the coil. In an office building, there's going to be like minimal outside air. It's just going to be, your people and your square footage load per code. There's not a significant exhaust here. And, we're going to have low sensible heat ratios because there's not a lot of latent load in our space, right? There's no like swimming pool, and it's not a cafeteria or kitchen where lots of food is giving off a lot of moisture. It's just really people as your latent load in your space here. Maybe a few small coffee machines and water fountain, but those are very, very low latent loads. So your sensible heat ratio is going to be very close to 1. And then you want to have an energy efficient system. This owner wants to hit a target. So what outside air system are we going to use here? Let's use an ERV, right? We don't necessarily have a huge we don't have a huge latent load in our space, right? And the outside air is going to mix with the return air. And we know that the outside air can be tempered slightly to 81. And then if it mixes with a 70-degree air, the entering coil of condition is going to be somewhere in the 70-degree range, 75, 76-degree range, which is right in line with what a regular central air handling system can handle, right? You can have a larger coil on your air handler if it's sitting in a mechanical room, so it can handle the latent loads that a VRF system can't. So we can get away with just using an ERV in this situation, tempering it only slightly, using that free cooling and free heating in order to allow the system to properly reach its set points, right? You don't need the DOAS system to totally dehumidify it because our air handling units can already do that dehumidification, that last step of dehumidification we need. Example D, we have a clean room lab, right? It's 8,000 square feet, so relatively small, but these clean rooms and labs have high exhaust CFM requirements, right? All these other examples were dominated by the code minimum requirements of outside air, but this situation, right? If we're pulling out all that exhaust air, we need to have a lot of outside air to make up, right? We want to maintain neutral mass balance. We want to balance our air coming in and air coming out. We're going to have a lot of outside air relative to return air in this situation. And with clean rooms, you have tight temperature and humidities. You can't, let's say it's a pharmaceutical clean room, right? You can't have, the compounding of the drugs. Those powders and, liquids, they can't get humid, or they can't get, they have to be perfectly precise in the temperature and humidity ratio that you have. And then a clean room, it's a small one. Maybe they want to hit some energy efficiency targets. So what do we need in this situation? We definitely need a DOAS, right? Because we have those tight temperature and humidities. But because we also have energy efficiency target, why don't we add in an ERV upstream of our DOAS unit, right? We can make a combined energy recovery wheel and DOAS unit. It's one unit that has both. And essentially that'll lower that temperature 95 down to 81. And then your DOAS unit doesn't have to handle 95. It can handle that 81-degree temperature. Let's see, downsize it a little bit and save operational and energy costs on this system. All right, and we're coming to the end of the presentation. So just a quick summary, revisiting that promise that I made to you guys in the beginning, right? I told you we're going to introduce those outside air systems. There's the 3 that we went over today are our outside air fan, our ERVs, our energy recovery ventilators, and our DOAS units, right? Maybe we do a combination of the ERV and the DOAS, but essentially those are the 3 levels. And then if we go on to, right, our next promise was, let's take a look at all these in a deep dive. What do these look like on a psychrometric chart? Definitely go watch that captive air video on YouTube. It's very, very helpful. We didn't really dive too much into it, but it might make a little bit more sense. You can see all of these air conditions on your psych chart, and you can tell from mixed air and your sensible heat ratio exactly where your entering and leaving air temperatures need to be in order to get a space temperature that's comfortable, right? For our human occupants, or if a warehouse, just your storage, boxes. And if it's a clean room, your pharmaceutical drugs or compounding needs to be in that tight range. You can figure out exactly what that temperature of your supply air needs to be with the psychrometric chart. So it's a very powerful tool you have as an engineer. And with those 3, each one of them has an advantage and disadvantage. your outside air fans, your ERVs, and your DOAS unit are all different levels of tempering or conditioning your air. And lastly, we looked at those examples, right? We looked at a few different versions of what an outside air system could look like based on the type of project you have. So that's our outside air systems. Let's look at some questions. All right, question number 1. What single check most directly decides whether outside air can be left untempered or if it must be tempered before a downstream coil? A, the mixed air condition versus the coil entering air temperature window, the total installed cooling tonnage available, the outside air dry bulb temperature only, or D, the supply fan static pressure at the design. So I'll give you a second to reread this. It's a little bit of a deeper question. What single check most directly decides whether outside air should be tempered? And the answer is A, the mixed air condition versus the coil entering air temperature, right? So this is kind of inferred from what we talked about, right? If you are mixing your return air with the outside air fan, maybe that's your first check, right? You mix that 95 degree, you find that tie line, that line on your psychrometric chart when you mix them. If you can achieve a temperature that's within, we'll talk about VRF, you can achieve a temperature that's, removed enough moisture with our VRF entering air temperature range, then maybe you don't have to temper the air. But if you mix your return and your outside air temp and you're nowhere near the temperature you need to be before you reach the VRF, you're going to have to cool it down. DOAS is the solution. So on to the next question. What is the key heat transfer difference between an HRV and an ERV, right? We have a heat recovery ventilator and an energy recovery ventilator. I think I mentioned this a little bit earlier, but maybe we'll read through the questions, the answers here. An HRV moves only sensible, and an ERV moves both sensible and latent. B, an ERV moves only sensible, and an HRV moves both. C, an HRV uses refrigerant, and an ERV uses water. And D, an ERV needs a reheat, and an HRV never needs it. So give you guys a second. The answer is A, right? And so we kind of talked about the wheels versus the plates. An HRV, those airstreams never touch, and so there's no moisture transfer across the exhaust and the outside airstreams. So that's a sensible only, right? It's A. And our last question, why does a DOAS dehumidification coil usually require reheat downstream? A, the coil overcools the air to wring out the moisture. B, the coil cannot reach the dew point without it. C, reheat is needed to raise the outside air CFM. Or D, recovery wheels always demand a reheat stage. Give you guys a second. And the answer is A. All three answers were A. So the coil overcools the air to wring out the moisture. Yeah, right. If you are dumping that really, really cold air because we need to, right? Our coil is very, very cold to get rid of the moisture, but it also makes your air sensibly super, super cold. Your dry bulb temperature is very low, and there's risks of having condensation in your space. So the answer is A. You're going to want to have reheat if you wring out the air and you overcool it. So that's it. Our presentation today was DOAS, outside air, and ventilation systems. Next week, we'll be talking about gas detection fundamentals. So yeah, this recording is going to be on our website, so check that out later today. And last three topics are already posted there. So have a great day, everybody. Thank you.